If you were asked to expand this, how would you do it efficiently? That is the motivation for this video. I will go through the discovery of the patterns that appear and offer explanations, and in the process discover the binomial theorem. I will spare you the tedious algebra and just display the first 5 terms in the binomial expansion in a pretty peculiar arrangement. What I want you to do is focus only on the powers x and y have. Do you see some pattern here? I will make it a bit easier. So now what we have is completely equivalent. However, I have displayed the powers of x and y even when they are 0 and 1. If you look at the first term in every row of the triangle, you can notice that something is in common. The x shares the same power as the binomial in that row, while the y always starts at 0. Then in the subsequent terms, the power of x decreases by 1, while the power of y increases by 1. This can be modeled by just summing from I to n, where n would correspond to its row in the triangle, and I would be its index in that row. Here is an example of how the powers match using the summation that we just found. Now that we found the pattern in the powers, let's head back to the triangle and see if we can find the pattern in the coefficients. What's common between all the coefficients? We can see that it's generating Pascal's triangle. So, if we wanted to know the coefficients at any row, we could sum the adjacent coefficients in the row directly above it. So, why does Pascal's triangle show up here? This is because of how we find the rows. We can see that to get the next row in the triangle, we can simply multiply the previous row by x plus y. If we distribute the x and y, we can see that the overlap of like terms is what causes the coefficients to be the sum of the adjacent ones. Informally, the multiplication of x and y kind of mixes it up. Now, to find the coefficients in subsequent rows, it would be pretty inefficient to multiply previous rows by x plus y. So, this begs the question, is there a better way of doing this? It is for that reason I will introduce some new notation that is called the binomial coefficient. So, what the binomial coefficient gives is the number of subsets of size I of a set of size n. For example, if we had a set that contains the numbers from 1 to 4, and we wanted to know the number of subsets of size 1, we can see that there is 4 of these in total. We can also use it to figure out the number of ways to build something when order does not matter. For example, if we wanted to know the number of ways to create x cubed y to the first from x plus y all to the fourth, we could instead think about it as the number of subsets of size 1 from a set of size 4. Here is all the possible ways to create x cubed y to the first from x plus y all to the fourth. We could select y last, or we could select it third, or second, or first. The 4 at the bottom is the coefficient that this term would have if we expanded the whole thing. So, the coefficients are simply the number of ways to create that term. If we add back the binomial coefficient into the summation, we end up with the binomial theorem. Lastly is the proof. We will use proof by contradiction. So, we will assume that the binomial theorem is not always true, which means that there is at least one power that the binomial theorem won't hold for. Because it is a positive integer, we can use the wet ordering principle. So, we can say that n is the least power where the binomial theorem does not hold. So that means x plus y to the n minus 1 has to be true because it is less than n, and also because it is trivial to show that n can't be 1. So, because this equality holds at n minus 1, if we multiply both sides by x plus y, then the equality will still be true. If we expand the summation and multiply in both x and y, and then group like terms, we can use this equality. This implies that the binomial theorem is true when we have a power of n. However, this is a contradiction. I would like to thank everybody that made it to the end of this video and would greatly appreciate a subscription and a like so that I can continue making content in the future.